Hi, my name is Kelsey Pratt, and I'm the project manager of JKLM Engineering. This semester, my team and I worked on the preliminary design of Shaw Lane reconstruction and Shaw Power Plant renovation project. Additionally, our environmental engineer, Kalissa, has worked on an off-site project pertaining to a PFAS treatment system. She will be discussing that at the end of this video. All right, let's meet the team. So, like I said before, I'm Kelsey Pratt. Calissa Clausing is our environmental engineer. Mitchell Walton is our geotechnical engineer. Jason Siegert is our structural engineer. Michael Picaro is our transportation engineer. Jamie Jordan is our pavements engineer. And we have Liam Conlon is our hydrological engineer. Okay, some site background information. We have the power plant located in the central part of Michigan State University's campus. It's adjacent to the iconic football stadium. It was constructed in 1948 and it was decommissioned from power production in 1975. It used to have a large smokestack that was removed in 2011, and the reconstruction and extension is part of MSU's campus master plan. The redesign of Shaw Lane is to accommodate the new learning facility. And as you can see in this picture, these are the site boundaries of which we will be designing preliminary work for. Hey, we have project requirements, which include the renovation and expansion of the existing power plant building. We will be repairing the segment of Shaw Lane between Chestnut Road and Red Cedar Road. We will be doing intersection configuration between South Shaw Lane and Red Cedar Road. We will be designing a stormwater sewer system for the new STEM academic building, analyzing efficient PCB remediation efforts that were taking place on the site in the 90s, concurrent with MSU Campus Master Plan. Implementation of sustainability and green infrastructure will be key components in our preliminary design. We're going to be ensuring that all rules and regulations are met, along with a cost estimation based on proposed work. Okay, so the impact of engineering solutions were definitely key components in this design. First and foremost, we wanted to consider the society, and we need to consider to determine if we're meeting the stakeholders and community needs. By doing so, we will be hosting public meetings every 9 months to determine if we are increasing the community livelihood by our new infrastructure. We'll be conducting surveys for students and faculty. By adding a new STEM building, we will meet the growing needs of MSU students in STEM majors and provide them with the skills that are in high demand in the workforce. Our sustainable solutions, we will be using efficient use of natural resources such as energy, water, and materials. Our infrastructure integrity will support the current and future generation needs. Our design will control stormwater and reduce impact to the Red Cedar River. Our green solutions include using recycled materials from MSU's Recycle Center, such as recycled asphalt. It reduces the carbon footprint since we won't be needing transportation costs since we'll be getting the materials from Michigan State. And our design considers PCB remediation that took place on the site, therefore less exposure to harmful chemicals will occur. Our economic solutions include boosting the economy to bring in at least 2-year construction jobs. Our green infrastructure is more cost efficient than traditional infrastructure. Our sustainable and green solutions will reduce water usage and cooling cost, and our new infrastructure can potentially increase property value by overall increasing the campus and education value. And now I'm going to hand it off to Calissa, who is our environmental engineer, and she will be discussing PCB remediation efforts that were handled on the site.
Hi, my name is Calissa Clausing, and I'm the environmental lead at JKLM Engineering. The environmental scope consisted of a PCB literature review. This was to determine how PCB mitigation was handled on the site by investigating previous remediation efforts, as well as a design of a granular activated carbon water treatment system for the removal of PFAS. This was an off-site project. PCBs are man-made organic chemicals. PCBs were created in 1920 and were banned in 1979 due to the concern regarding negative health effects. PCBs have been found to cause cancer, as well as other adverse effects. Due to the Toxic Substance Control Act, PCBs have 3 different action levels. The first is less than 50 ppm. The second is 50 ppm to less than 500 ppm, and the third is equal to and greater than 500 ppm. At Shaw Lane Power Plant, there were 2 sites that had PCB contamination greater than 50 ppm. Remediation occurred in 1994. The dots on this map to the right are the soil borings to indicate if there was contamination, and the circled regions are where the contamination occurred. One contaminated site was near the sidewalk. PCB concentrations were greater than 1 ppm. The area of concentration was 85 feet by 40 feet, with a maximum depth of contamination being 11 feet. The highest recorded PCB concentration at this area was 1,100 ppm. At the other locations within the area, the PCB concentration was greater than 100 ppm. The second contaminated site was near the south side of the power plant. PCB concentrations were greater than 1 ppm. The area of contamination was 120 feet by 90 feet, with a maximum depth of contamination being approximately 5 feet. At both locations, the cause of contamination was unknown. Between both sites, approximately 295 to 375 cubic yards of soil contained concentrations greater than 50 ppm. The contamination was disposed of at Heritage Landfill. It was also approximated that 1,200 to 2,040 cubic yards of soil had PCB concentrations greater than 1 ppm and less than 50 ppm. This contaminated soil was remediated based upon the Act 307 Type B cleanup criterion. Based upon the action letter submitted by Michigan State University, this is the list of bidders for the remediation efforts. Environmental concerns. Groundwater samples were collected from wells that extended across the water table and were down gradient of the sites with the highest contamination. The water samples did not contain detectable concentrations of PCB. There are no concerns regarding PCB in the drinking water. There are also no concerns regarding the PCB remediation efforts conducted. There are no economic concerns regarding the remediation for the Shaw Lane Power Plant project since the remediation has already occurred along with the payment of the remediation. PCBs have 3 different action levels. Since the contaminated locations have been mitigated, the Shaw Lane Power Plant is able to move forward with construction. Up next is Mitch, who will be discussing the geotechnical portion of the Shaw Lane Power Plant.
Thank you, Calissa. As mentioned before, I am Mitchell Walton, and I am the geotechnical engineer who designed JKLM's foundation for this project. The scope of geotechnical work was to design a foundation that would most effectively support the proposed western and southern stem buildings. In order to complete this design, a geotechnical investigation needed to be completed and reviewed. Design soil profiles had to be created from this investigation. Design loads had to be quantified by the structural engineer. Design considerations needed to be evaluated. A foundation type had to be selected. Then once selected, this foundation had to be designed. And finally, a cost estimate needed to be generated. In order to begin, a geotechnical investigation had to be completed. Thankfully, MTC consultants had completed a geotechnical investigation for MSU in 2018 that was used by JKLM. MTC provided 13 total soil borings throughout the project site. The graphics showing the soil borings completed by MTC can be seen on the right of the slide here. These soil borings show a strong mix of sand and clay layers that range from elevations 805 to 848. Numerous of these layers were identified as weak layers, and a high groundwater table elevation was found that varied between 4 to 12 feet below existing grade. Also noted was a layer of shale bedrock that began approximately 30 feet below existing grade. The high groundwater table elevations can be seen here and here, and the start of the shale bedrock can be seen here and here. Up next was to create design soil profiles from these soil borings. A western and southern alignment were created to show the representative soil layers that would lie beneath the western and southern buildings. As seen on the figure to the right, the western alignment would include soil borings B3, B4, and B5, And the southern alignment would have soil borings B5, B6, B8, and B7. Soil layers were simplified into horizontal layerings by combining non-cohesive and cohesive soils. On each of these horizontal layerings, as can be seen here, the weakest friction angle for sands or shear strength values for clays were used to represent the entire layer for conservatism. Next, the building weight and column layout were determined by Jason Seeger, who is the structural engineer at JKLM. Approximate column loads and column layouts can be seen on the right of the slide here. The heavier southern building, which weighed a total of 18,159 kits, can be seen here with its column layout, and the lighter western building weighing a total of 13,579 kits can be seen here with its column layout. On this project, there were many different design considerations. The main consideration for design is the existing Shaw Lane power plant. In order to reduce complexity of construction and risk damaging the existing foundation, the proposed foundations and buildings were designed to be 20 lateral feet away from the power plant. This separation will reduce the concern of losing restraining lateral earth pressure for the existing foundation and will not require complex retaining structures to be necessary during construction. The second consideration is a high groundwater elevation at the site. A high groundwater table creates concerns with buoyant uplift and basement leakage. So drainage will be required adjacent to the foundation, and the exterior basement walls will have to be waterproofed according to section 1807 of the Michigan Building Code. Next to note is the existence of numerous weak soil layers in the design soil profiles, and these weak soil layers exist right near the bottom of the proposed basement. Finally, a strip footing would be designed to support the exterior walls of the building. These walls are non-structural, and the footing will just need to handle the self-weight of these walls. Now is time to select the appropriate foundation type for this project. JKLM chose to utilize a pile foundation. Piles were selected because they could bypass the weak soil layers and transfer the building loading onto the shale bedrock. This strong bedrock layer was calculated to allow less than 1 inch of elastic settlement. So there's very little threat of high and or differential settlement. Piles will also require less excavation, which will help to not spread contaminated soils below the site and make it easier to not disturb the existing Shaw Lane power plant and its foundation. Piles are also quicker to construct, which will allow students and faculty to make use of the new academic buildings sooner. Cast in situ piles were selected over driven piles because of concerns of creating vibratory damage to the power plant foundations and creating high noise levels on campus. Now is time to design the pile foundation. Using the building loading and the allowable bearing capacity of 30-foot long, 18-inch concrete piles, 2 separate pile configurations were designed. The heavier southern foundation was designed with 55 piles, and the lighter western foundation was designed with 40 piles. The spacing of these two pile designs can be seen on the right of the slide here. The width of the strip footing needed to support the self-weight of the walls from the 5 stories was calculated to be less than 1 foot. But according to section 1805 of the Michigan Building Code, it was required to be constructed at a width of 1 foot. Finally, JKLM estimates that the price of installation of the 2 pile networks with a total of 95 18-inch piles will cost approximately $850,000. Next up will be Jason to talk about the structural design of this project.
Hello, my name is Jason Seeger, and I am the structural engineer for JKLM Engineering. The goal for this part of the design project was to design and analyze an academic building that will be placed next to the Shaw Lane power plant as an addition. Over the next few minutes, I will be discussing the created layouts of said building, the loads and load combinations that the building will be subjected to, an analysis of the structure, built member design, and cost estimation. Shown here in these figures, there are very specific guidelines and minimum requirements supplied to us by Michigan State University. Requirements include faculty offices, different sizes of classrooms, computer labs, laboratories, and stairs, bathrooms, and elevators that all need to be placed in the building. This building will be 4 stories tall with a basement and will be placed in an L shape that is split at the southwest corner with walkways in between the 4th and 1st floor for easy access, as shown in the figure. And for simplicity's sake, the buildings will be referred to as Building 1 and Building 2. Here, we have architectural layouts for Building 1 on the right and Building 2 on the left, each showing how the minimum requirements described earlier will be met. A few extra additions were added, such as a coffee shop and some extra storage areas to accommodate for the empty space due to the minimum requirements. Building 1 will have the structural layout here as shown. Its dimensions are 80 feet by 200 feet, and along the 80-foot side of the building, there will be 4 sets of columns, with the 2 interior frames 29 feet away from the exterior of the building, as shown here on the left. Looking at the 200-foot side, the columns will be spaced at an even 25 feet throughout. And the column height for the basement floor will be 14 feet, and for each floor above that, the columns will be 13 feet tall. And each floor, including the basement, will hold a 6-inch thick slab that will run through the span of the entire building. Building 2 will be very similar to the layout in Building 1, with the only exception being that it is 80 feet by 160 feet rather than 200 feet, which causes the beam spans to be a little different. As you can see here on the figure on the right, the two beams at the ends will be 30 feet, and every beam in between will be 25. And also, highlighted in red will be bracing frames, or bracing members rather, that will be placed on the exterior of both buildings to provide stability for the structures overall. The loads considered for this project were live, dead, wind, snow, and roof live. Seeing as the site resides in Michigan, earthquake loads and etc. will not be included. Also, for the sake of time, only 3 load combinations were needed to input into the analysis of the structure, and these combinations are presented here in the table below. For the analysis portion of this project, a structural engineering program named SAP 2000 was used to determine the internal forces displayed by the members because of the load combinations that are acting on each building. These forces were then gathered and used to finally design each member. Due to the time constraint, only Building 2 was modeled in SAP, but because these two are so similar, Buildings 1 and 2, the internal forces will also be very similar. 2 columns were designed, one for columns that are loaded with a force of 400 kips and below, and one for columns that are loaded between 400 and 700 kips. Also, a beam, truss, and bracing member were each designed using the maximum internal forces displayed by each respective group that were found in the analysis portion. And the final selection for each member are shown here, along with the cost of each of the 5 members that were designed. Adding together the total cost of the members, along with each slab and other engineering fees, the total cost of the structural element for this project will be approximately $6,272,180.50. This concludes the structural aspect of the presentation, and next up is Michael, who will be discussing the transportation area of this project.
Hi, I'm Mike Bercaro, and I am the transportation engineer for JKLM Engineering and was responsible for the transportation aspects of this project. The overview of this project basically includes our initial transportation proposal and then an analysis of the intersection and the capacity, then a redesign using a CAD program, and additional design elements, and lastly, a cost estimation of some parts of the project. To begin, as per the master plan, MSU's master plan, we want to become a more bike-friendly campus, so we're going to get rid of North Shaw Lane in terms of vehicle access. Instead, we're going to turn North Shaw Lane into a dedicated two-way exclusive bike facility. What this means then is that we have to expand South Shaw Lane to absorb all of the traffic that can no longer go on North Shaw Lane. We're also going to have to reconfigure the intersection of Shaw Lane and Red Cedar Road. Here are the design criteria I used. The design vehicle is a 60-foot articulated bus, which is probably the largest common vehicle on campus, especially given the proximity to the CATA bus station on campus. And there's the design speed of 30 miles per hour. And as per MDOT recommendations, a posted speed 5 miles less than the design speed was factored in. So hence the 25 mile per hour speed limit, and a cross slope of 2% and a maximum grade of 3%. So before we could actually reconfigure the intersection or redesign the roads, we had to kind of get a gauge of the growth rate and the capacity of the intersection. So looking at MSU enrollment data and using the Tri-County Regional Planning Commission website, we found a growth rate of about 1%, but we rounded up to 1.5% to be conservative. And so that means for a design year of 2040, this turns to a growth factor of 1.35. So given traffic data counts provided by Iteris Vantage Live, we multiplied these counts for all the different turning movements by this growth factor to get our 20-year projection. And it was these 20-year projection values that we put into Synchro 6, which is a traffic modeling software. So after testing out a whole bunch of different configurations, including and excluding left turn lanes and different permitted movements, this was the optimized signal timing for the given traffic counts. We have permitted lefts on Red Cedar Road, and then right turn on green is allowed for both roads. And here's the phasing information. And then for South Shaw Lane, we have a permitted plus a protected left phase, which is actually right here. So the left turns will be protected for 17 seconds, followed by a permitted phase for all movements on South Shaw Lane for 37 seconds. And the total cycle length is 90 seconds, which is increased from 75 seconds. With this information, I was able to completely redesign the intersection to accommodate the new signal timing and the increased traffic from our projection. As mentioned earlier, here is the cross section with a cross slope of 2%, and this is a cross section of South Shaw Lane at its widest point right before the intersection. Here's a little bit closer view of the intersection. It's kind of hard to see, but we have included signage and pavement markings and dimensioning. And here's a closer look at the pedestrian and bicycle facility crossing. This is going to be activated using a pedestrian call button, so it is not super intensively planned within this synchro modeling, since it can just be activated with the call button. Here is a northwest view of the intersection, and here's a southeast view of the intersection. And we'll discuss kind of the geometrical elements in the pavement marking in the following slides. So we made sure that all of the turning radii for the intersection would be appropriate for a bus. And so the minimum radii for that is 21.5. As you can see, all of them are at least that distance. And the lane widths are 10 feet as per MSU design standards. And you may have also noticed that all approaches include exclusive left turn lanes. This was found to provide the greatest level of service for the intersection as proven through the synchro analysis. Down here, you can see all of the pavement marking, dimension details, and this was informed primarily through the Manual of Uniform Traffic Control Devices. Beyond the scope of the transportation aspect, we did include some additional design elements. This includes the complete removal of lots 39 and 40. This is done because we already have to kind of encroach upon lots 39 and 40 to widen South Shaw Lane. So in an effort to promote a more sustainable, green, and pedestrian-focused campus, we're going to get rid of lots 39 and 40, a total of 4.36 acres, and replace it with a green space. And this will include landscaping, benches, trees, so on and so forth. And it will be a nice central spot in campus for students to relax and enjoy recreational activities and picnic and all sorts of fun things. But in order to, you can't just rip out a parking lot and then call it a day. So we are going to convert parking area 56 into a multi-level parking structure so as to absorb the 549 spots that are going to be lost from the conversion of this area into a green space. Factoring in all of the parking spots from lots 56, 39, and 40, and then multiplying it by our growth factor of 1.35, we know that this is going to have to be a parking structure that can accommodate 950 total spots. This is an advantageous location because it's hard to see, but off in the corner is the stadium. So this area can provide additional stadium parking on game day, and it will just allow more parking in a smaller amount of open space. Lastly, here we have the cost estimation. This does not include any construction costs or traffic lights and their supports. This is primarily just the pavement markings and the signage. The pavement marking information was informed through the 2019 MDOT weighted average item price report, and the signage information was primarily informed through a manual of traffic signs online. And so summing these two costs together, the total cost for pavement markings and signage for this project is going to be just under $83,000. Here are the references I consulted when doing this design. And up next, we have Jamie, who will discuss the pavement design of this project.
My name is Jamie Jordan, and I conducted the pavement design for this project. The scope of the pavement design included investigating the existing pavement conditions, evaluating the pavement distresses that pose to be problematic, creating a design to rehabilitate portions of Shaw Lane, staking out the area of pavement to be removed, and creating a new design for a new roadway to be installed. The final portion of the scope was to estimate the cost of all of the above things listed. So we started with a site investigation conducted on Shaw Lane by taking pictures of the distresses and documenting their locations. The existing road is an asphalt pavement and clearly appears to be approaching its wear life. All of the distresses were assigned a number, and that number was placed on an aerial photo to identify the location of where each distress was at. Looking at the photo on the left, the frequency of distresses can be seen along the western portion of Shaw Lane, starting with number 1 at Chestnut Road and having the numbers increase as it gets closer to Red Cedar Road. Looking at the photo on the right, distress number 1 is there. This is at the westernmost side of Shaw Lane at the intersection of Chestnut Road. As you can see, there's clearly evidence of longitudinal and transverse cracking, likely attributed from low temperatures and the age of the pavement. As we continue to move east along Shaw Lane from Chestnut Road, the distresses appeared to show similar trends. there is still evidence of transverse and longitudinal cracking, along with some block cracking in certain areas. The pictures shown on this slide are located at distress number 32 and number 35, which lies roughly 300 feet before Shaw Lane breaks into a north and south divided roadway. To continue the investigation, we approach Red Cedar Road. More of the same types of cracking can be observed. There is some evidence of fatigue cracking, but it is the least prevalent of all of the types of cracks that have been stated before. Much of the road's roughness can be attributed to the black and low temperature cracking. The low temperature cracking, the black cracking, and the initial phase of this fatigue cracking are definitely the most concern in this design, as they tend to lead to potholes and subgrade issues as they continue to develop. At this stage, permanent deformation and drainage issues are not prevalent, as there's really no evidence of excessive rutting. The distresses that have been observed likely are caused by aging, freeze-thaw cycling, and oxidation due to exposure, and none of it really reflects any structural insufficiencies. To be able to further investigate the condition of the existing pavement, coring samples would be required, but for this application, I'm estimating that the distresses don't go to a depth greater than 3 inches to proceed with the design. The geotechnical investigation also was considered in my pavement design by looking at soil borings B5 through B8 and the soil profile created as well. Profiles B5 through B8 are on the southern alignment of the boring locations, which lie closest to Shaw Lane. As stated before by our geotechnical engineer, a mix of sand and clay layers were found and numerous weak soil layers were identified. So these soils are not optimal in the use of roadway construction, and new material will need to be hauled on site for new construction. After evaluating the distress report, it was decided that Shaw Lane would be rehabilitated between Chestnut Road and Red Cedar Road. The plan sheet on the left shows roadway dimensions from the Chestnut Road intersection all the way through station number 7. And the plan sheet on the right shows stations number 7 through number 14, which ends at Red Cedar Road. The design of this portion of the road consists of doing a full width mill of the asphalt surface to a depth of 3 inches to alleviate all of those cracks discussed before. The milled pavement will then be replaced with 1.5 inches of 5C modified surface course and 1.5 inches of 3C modified leveling course below it. This is to follow the guidelines established by Michigan State's Infrastructure Planning and Facilities Department. By replacing the top 3 inches of the pavement, it'll really reinforce the structurally sound base and renew the ride quality of the top of the road as if it were already new. For the eastern portion of this project, there will be pavement and earth removal required of lot 39 and lot 40. This is required to extend the width of the road, add the new bike lane, and add the 190,000 square feet of green space. Looking at the plan sheet on the right, you can see a yellow crosshatch section. This area identifies the space needed for widening South Shaw Lane. An excavation will need to be dug 14 foot deep along the entire north edge of South Shaw. The width is 37 feet from the inside of the gutter, extending 100 feet at intersection approaches, and then the width tapers down to 25 feet from the inside of gutter on the straight portions of road. The parking lots number 39 and 40, just north of them, a 4.75 inch undercut will be required to place the permeable bike lane. The dimension plan sheets for the eastern portion of the project are located here. On the left, we have stations 15 through 18, and on the right, we have stations 18 through 26. The existing pavement on South Shaw Lane is to undergo the same mill and fill technique as performed on Shaw Lane west of Red Cedar Road. And the new pavement will butt up at the same elevation as that fill. So to begin the new construction, we'll start with 8 inches of 21 AA aggregate to be compacted in lifts where the existing soil has been removed along the north edge of South Shaw. A curb and gutter detail is located here on the right. The curb will contour the north edge of the new road following the campus master plan for curb details. And asphalt will then be replaced between the existing road and the new curb with 3.5 inches of 3C modified leveling course and 1.5 inches of 5C modified surface course. Moving on to the final pavement portion of this project is the porous pavement bike path. This will follow the 4.75-inch undercut that is north of lots 39 and 40. It extends between Red Cedar Road and Farm Lane. As specified in this plan sheet on the right, the undercut is to be filled with 2 inches of reservoir course, 2 inches of filter course, and 3/4 of an inch of porous asphalt course. And that will sum up all of the pavement on this project. So finally, we'll get to the cost estimation. Each item is broken down on the left column with its associated unit cost and the column next to it. The quantities of each item are listed in the third column with their corresponding unit. And in the last column, we have the total cost of each item with the summation at the bottom coming in just under $200,000. That finishes up the pavement design of Shaw Lane reconstruction. And next up is Liam to discuss the hydrology aspects of this project.
Hello, my name is Liam Conlon. I'm the hydrology specialist here at JKLM Engineering, and I will be talking today about the hydrological aspects of the Shaw Lane repurposing project. So a little bit about the scope of the hydrology team. The primary objective is the design of a stormwater management system to prevent flooding and effectively convey stormwater on the site. And this consists of the design of a retention pond and sewer systems to store runoff from these storm events and the implementation of sustainable low impact design features. All of this while following the rules and regulations at a university, county, state, and federal level, and while being sustainable and cost effective in its design. And while designing these systems, you have to be aware of the overlap between other technical specialists. So some examples of overlap is that I need the soil analysis for the determination of imperviousness constants, which I get from geotechnical. I have to coordinate the building of some of the low impact design features with the pavements as they are part of both systems. And I have to coordinate the placement of a retention pond and piping and other impact features with structures so that it doesn't interfere with the foundation of the building. Some of the rules and regulations of the stormwater system. So the Ingham County Drain Commissioner stormwater rules and regulations are the basis of the design for this system. It tells you what kind of storm events you're looking at, what kind of design features need to be implemented, and what are the restrictions for the design. Michigan also requires a soil erosion and sediment control. So we have to have erosion controls built into the design. There needs to be routine maintenance built into the design. And you need to acquire an SECS certificate of training for this aspect of the project. There's also EGLE, flood hazard management permits that need to be acquired. So for this project, we need a wetlands protection permit and an inland lakes and streams permit. So this is the proposed stormwater system. This is the plan view of it. constructed in AutoCAD. So the total site area of the project is approximately 10 acres. It's 10.0551 or something. And on this site, the largest accumulation of runoff that would occur is in the Spartan Stadium parking lot, which is included in the project area. And the entire stormwater design system consists of a retention pond, implementation of new stormwater piping systems, and the implementation of several low-impact design features. So you can see some of these features in this plan view. In orange, we have our retention pond. In green, we have several bioretention centers. In yellow, we have a permeable parking lot that replaces the current parking lot on Spartan Stadium. And in blue, we have a vegetative swale, and in red, we have a permeable bike path. And the emphasis of these low impact design features, the permeable pavements, the bioretention centers, and the swale, are to combat low infiltration rates by providing temporary storage and replacement of some soil to help improve infiltration. This is the proposed pipe network layout. It consists of about 12 piping sections that all eventually flow into the retention pond. And here I have the invert elevations, just so we know what kind of slope we're looking at and where the water will end up, and if we have to change the elevation of the water as it flows into the retention pond. So the retention pond is designed to handle the volume of 2 consecutive 100-year 24-hour storm events. This covers about 0.5 acres of space on the site, and it is a trapezoidal prism shape with the side slopes of 4 horizontal and 1 vertical as outlined by the Ingham County Drain Commissioner. And there is another requirement of the Ingham County Drain Commissioner that there needs to be a vegetative hold. So for this system, we're using flat stem bulrush as it is considered a native species, and it provides some safety for the participants of this system. So here's a top-down view. It shows that there is in fact a side slope, and it shows the kind of scale of the retention pond. It's got 258 width, about 150 height, or length in this case. So some of the LID features that are implemented in this site, there are 3 specific different ones that focus on the storage and improvement of infiltration on the site. So it improves infiltration by inclusion of new soil that is better suited to store water, and the introduction of local vegetation to these features that help to beautify the campus as well as to reduce runoff. And ideally, these are working in conjunction with each other to deliver and reduce stormwater runoff. So for example, the vegetative swale works with the bike path, the permeable parking lot works with the bioretention centers, and these all end up flowing into the retention pond if there's any extra overflow. So here are some cross sections of these LID features. So we see a permeable parking lot that has a storage capacity in the blue of about 16 inches, and it has and the total area of the parking lot is about 4.33 acres. So that provides quite a lot of storage for water, and it also helps to filter the water. And also within this parking lot area, there are these bioretention centers that have 4 feet of storage of new soil, of bioretentive soil, and as well as providing vegetation. And the inlets for the sewer pipes in this system lead into the bioretention centers, so it helps to divert water that way. Here's a cross section of the vegetative swale and the bike path, which are located next to each other. So the vegetative swale has side slopes of 3 horizontal, 1 vertical, and a depth of 2 feet. And these 2 run next to each other and help to divert stormwater. The soil replacement is also a depth of 4 feet and covers about 800 linear feet on site, and the permeable bike path has a length of about 1,100 linear feet in this site. A little bit about cost for this system. Each of the individual costs are presented here, but the total cost of the system, including construction and including recurring costs, or not including recurring costs for this system, is $3.19 million. And a little summary of the entire project. The cost of installation is the $3.19 million as discussed before, but there are some recurrent costs that you need to take into account. There is erosion and sedimentation control costs of about $55,000 a year. There's a landscape maintenance cost for these systems of about $71,000 a year. And overall, the system is safe. It helps to prevent flooding. It can help control large-scale pollution and reduce stormwater, as well as small-scale pollution. And I think the large-scale pollution aspect is critically important due to the location and due to the presence of lots of people, lots of tailgaters, lots of pollution that ends up near the stadium. So it can help control and make this easier to clean up. And it is also aesthetically pleasing and provides a dual use of the critical space as a space for people to relax, to enjoy, as well as to help control runoff. And next, we'll have speaking Kelsey Pratt. She is the project manager for JKLM Engineering, so take it away.
Thank you, Liam. Now I'm going to discuss my role as project manager on this team. My role involved facilitating many subdisciplinary interactions. A schedule and communication plan were put into place immediately. Deliverable updates and progress reports occurred throughout the entire duration. Time management was crucial in order for our team to accomplish goals. Scope assessment occurred, construction schedule, and construction cost estimation. Okay, I'm going to go into the subdisciplinary interactions. Here is a diagram with me at the top and each team member. We have our environmental engineer over here who helped incorporate sustainable and green infrastructure into our design. Our hydrological engineer worked with our pavement engineer in order to incorporate permeable pavements, bike path, stadium parking lot. Our structural engineer worked with our geotechnical engineer. Our geotechnical engineer was entirely dependent on our structural engineer's design in order to complete the loads for the foundation. Okay, and then our hydrological engineer, transportation engineer, and pavement engineer all worked with each other to make sure each design was compatible with each other. Okay, and our sustainable solutions involve a stormwater retention pond, which will reduce stormwater runoff rate and volume, which will reduce the hydrological impact to the Red Cedar River. We have incorporated permeable pavements wherever possible. We have a bike path and parking lot to reduce runoff volume and slowly release it into the ground. We're using recycled asphalt that will be coming from MSU, so therefore it's a sustainable source of pavement materials along with eliminating waste, carbon footprint, along with decreasing transportation, miles traveled. Then we're going to go on to our bioretention. We are going to have rain gardens, a vegetative swell path to increase soil infiltration and control runoff. We will be using minimal site grading and erosion control practices, so we do not cause any kind of soil erosion to impact the ground and sedimentation. Okay, so our construction schedule involves 3 different phases, and each phase will have multiple parts within that phase. It's important to note that the schedule does consider weekends, holidays, any kind of event happening at the university, along with when school is in session. Okay, and here's an overview of it. I apologize that I couldn't get the full Gantt chart into this slide, but it is a very long one because the entire schedule consists of 3 years. Okay, so phase 1 involves project administration and framework. We want to complete the design, review bids, select prime and subcontractors, host public meetings, gather materials and equipment. That is all really important before we can just start the preliminary construction. And then we're going to go into phase A, B, and C, which you can see here: preliminary construction, prepare the site for any kind of construction taking place. We want to mark the trees, placement of the fence, brush removal, demolition of the power plant. And as you can see here, we're going to move straight into starting the stormwater sewer system because it does not need to wait for the building to be constructed. And then installation of the bioretention centers and the permeable pavement can happen all during these phases. Okay, and then we're going to move on to phase 2, which consists of phase D and E. We're going to have the power plant renovation and expansion taking place. It's going to take a little bit more than a year. As you can see, that is a pretty long duration. And then we have phase E with our street improvements. Then we're going to move on to phase 3, which is phase F and G, which is the intersection reconfiguration. And then we're going to do green space and a parking structure all in phase G, because we do not want to decrease the amount of parking spaces without having a parking structure in place. So construction and scheduling, this is our site plan. And as you can see here, this is phase A, B, and C. And then here's our permeable parking lot, our demolition of the power plant, and have some pavement removal because there is a parking lot adjacent to the power plant. And then we will be instructing our retention pond, vegetative swill path, permeable bike path is all along here. And then we will be doing pavement removal to prepare the intersection or for street improvements. This is going to happen. We're going to be removing the pavement before we go into the next phase. And we're going to work our way from Farm Lane, which is right here. And we're going to move all the way to Red Cedar Road and then finally to Chestnut Road. Okay, and then phase 2 involves power plant renovation and expansion and street improvements. As you can see, we're going to start our pavement removal in this phase so we can prepare for the next phase. And then here's our street removal. This isn't completely accurate. I just wanted to show what it will look like with the foundation getting in place and permeable bike path will right here, and just to get an idea of what kind of work is happening. And then in phase 3, we're going to move on to our intersection reconfiguration, green space and parking structure installation. And this will be the green space, our intersection reconfiguration, complete the building exterior, plant vegetation, and establish it. Okay, and now we're going to move on to our cost estimation. Okay, I do want to note here that this estimation is rather low. Our goal was to aim for 30 million, but it did not end up being that way. So there are a lot of costs included that were not included in our scope of work. So that is important to note, but our subtotal before the lump sum items is $11,872,078. And then including the lump sums, it comes to $14,157,453. And the final amount keeps getting cut off, but it is just over 16 million. And then we need to include our annual cost of erosion, sedimentation. So that will be $55,959 per year. And our annual cost of landscape maintenance is going to be $71,356 per year. Okay, and that's about it. So if you guys have any questions, please let us know. I know it isn't the same because it's recorded through Zoom, but we appreciate you listening and thank you. So now I'm going to send it over to Calissa and she will be talking about her offsite project, which is a PFAS treatment system. Thank you.
Hi, my name is Calissa Clausing, and I'm the environmental lead at JKLM Engineering. And I will be discussing the offsite project for PFAS remediation. The problem statement was to design a physical chemical treatment system for the removal of PFAS from an industrial source or from a wastewater resource recovery facility. The first step of the design process was to write an introduction on what PFAS are, the health concerns regarding PFAS, and popular treatment methods. As seen below are PFOA and PFOS, which are the most common PFAS chemicals, and their chemical compositions can be seen. PFAS is the broad term used to describe approximately 8,000 man-made chemicals that act similarly and are of similar composition. PFAS have been used in various industries for their stain resistance, non-stick, and waterproofing. The PFAS chemical characteristics consist of being very stable and extremely soluble. This allows it to travel quickly through the soil and into the groundwater. PFAS can cause negative effects after exposure. Various studies have shown that PFAS chemicals have altered kidney and thyroid function, along with endocrine disruption, carcinogenesis, immunotoxicity, and metabolic disruption. PFAS enters into the environment by industrial point sources and the resulting emissions re-entering surface water and groundwater, spillages and runoffs from incidents and locations utilizing firefighting foams, landfills, and wastewater treatment plants, and the application of contaminated biosolid. The 4 treatment methods for PFAS that we looked at were carbon absorption utilizing granular activated carbon, ion exchange, reverse osmosis, and nanofiltration. The second step of the design was to write a literature review on granular activated carbon column modeling methods, as this would be the type of technology that we would utilize moving forward. Models that were analyzed were Bohart-Adams model, mass balance relationship, scale-up approach, moving bed counter current absorption column, fluidized bed, and empty bed contact time. The last step was the technical design. A location needed to be chosen in Michigan that had PFAS concentrations higher than the legal limit. The location that was chosen was North Kent Sewer and Water Authority. This is the service area for North Kent Sewer and Water Authority, which contains multiple townships and the city of Rockford. Near the city of Rockford had previous contamination of PFAS from a shoe company. This is the current treatment plant at North Kent Sewer Authority. At 1 is the headworks. At 2 is where the bioreactors are. At 3 is membrane filters. 4, biosolid processing. 5 is UV disinfection. And then the clean water is discharged to the Grand River. A PFAS effluent monitoring report was submitted by North Kent Sewer Authority to the Department of Environmental, Great Lakes, and Energy. This report contained information regarding PFAS samples that were taken on February 3rd, 2021. The PFAS levels were monitored at the UV channel. As seen in this diagram, there are multiple PFAS chemicals that were recorded. The PFOS and PFOA were the only chemicals that were above legal limit. Therefore, they will be the focus of the treatment. This is a table of the flow statistics from leaving the UV channel. The average flow leaving the UV channel was 3.55 million gallons per day, and this will be the flow utilized for the calculations. Ideally, pilot scale testing would have been ideal for modeling the North Kent Sewer Authority treatment facility, but due to budgeting and resources available, empty bed contact time will be the best method moving forward. Since pilot scale testing was unable to be conducted, the paper Effectiveness of Point Use Point of Entry Systems to remove PFAS substance from drinking water will be utilized. The article had water characteristics that were similar to North Kent Sewer Authority. Therefore, the isotherm parameters that were utilized will be also utilized in the empty bed contact time calculations performed. The article also analyzed the effectiveness of 2 different carbon materials. The researchers determined that Evoqua 1230 CX was more effective, Therefore, Evoqua 1230CX was utilized in the design. Since Evoqua carbon was used, it was decided that Evoqua absorption column would be used as well. These are some given values from Evoqua Water Technologies. The pounds of carbon that an HP 1220 holds is 20,000 pounds. The density of the Evoqua 1230CX carbon was 450 kilograms per meter cubed. The diameter of the HP 1220 was 12 feet. And the flow rate for the HP 1220 could be between 500 and 1100 GPM. But after doing the calculations with both 500 GPM had an EBTC that was an acceptable value. And so 500 gallons per minute will be utilized in calculations. These were the equations that were used. This is a summary of the calculated and given values. The empty bed contact time was found to be 10.62 minutes. The service flow rate was 5.65 hours, and the linear velocity was 4.42 gallons per minute per feet cubed, or feet per second. And these all are within acceptable values. The total breakthrough time was a little over 1 day, and the cost per 1,000 gallons was 90 cents. The average flow of water leaving the UV disinfection channel is 3.55 million gallons per day. The 3.55 million gallons per day is greater than one GAC tank could service. Therefore, a frac tank is necessary to hold the water before it flows into the GAC system. The frac tank will then moderate the flow so that the flow into the GAC column is constant at 500 gallons per minute. With a flow rate of 500 gallons per minute entering the GAC columns, 4 GAC columns are necessary for the treatment of PFAS. One HP 1220 system comes with 2 absorption columns. Therefore, it is necessary to purchase 2 Evoqua HP 1220 systems to service the 500 gallon per minute flow. North Kent Sewer Authority needs to purchase 2 Evoqua HP liquid phase carbon absorption systems. The cost of these 2 systems is $560,000. Since each system holds 20,000 pounds of Evoqua 1230CX, a total of 40,000 pounds of GAC is required. The cost of this is $0 due to the carbon coming with the purchase of the HP 1220 systems. A frac tank is also needed to hold the water coming from the UV disinfection. A new or used frac tank can cost anywhere between $5,000 and $14,000. Piping and pumps will also be required to move the water from the UV disinfection channel to the frac tank, from the frac tank to the GAC columns, and then from the GAC columns to the Grand River. In total, the piping and pumps can assumed to cost $28,000. The cost of delivery and installation of the systems is $50,000. And lastly, before the systems are able to run, they must be prepped, and the cost of changeout and slurry is $108,000 for both systems. Therefore, the overall cost for a PFAS removal system for North Kent County is between $751,000 and $760,000. Environmental concerns. The disposal of contaminated GAC material is challenging in Michigan. Have a high temperature incinerator. Therefore, the PFAS contaminated material must either be shipped to a state that does have a proper incinerator, or another method of disposal must be utilized. In Michigan, there are some hazardous waste disposal sites. These sites might dispose of the contaminated GAC material. It is recommended that North Kent Sewer Authority reach out to the nearby hazardous waste disposal sites to learn about further protocols regarding the disposal of PFAS contaminated material. Other waste that is not removed by GAC will enter into the backwash stream. Therefore, it is important for this to be taken into consideration when implementing the PFAS removal system. Environmental recommendations. It is recommended that a pilot scale test be conducted to design a more precise system of removal. Within the empty bed contact time design, there were assumptions made using isotherm modeling that could cause room for error. Therefore, by conducting pilot-scale testing, the design will be more tailored towards North Kent Sewer Authority and better meet their needs. Alternative PFAS removal methods could also be conducted during the pilot study. For instance, carbon absorption using powder-activated carbon, ion exchange, or membrane filtration. This could help determine which method is the most successful and cost-effective. Ending messages. The PFAS treatment design can positively impact those living in the Kent County as well as those who utilize the Grand River. The PFAS removal can help ensure a safer environment and improved human health. Any questions?